So Nevin Lennon Bertrand will be speaking about gradualizing the calculus of inductive constructions.
Okay, let me share my screen. Okay, can everyone see this and hear me?
We hear you and see you.
Awesome. Okay, let me start this. Okay, so welcome to this third top class talk. As has been already mentioned, the aim here is to bring together two lines of research. On the one hand, we have the calculus of inductive constructions, and on the other side, gradual typing. So let me start with a little bit of context on this. So on the one hand, the calculus of inductive constructions. So most of you here know this probably. It's a language whose main feature is dependent types. Here, for instance, you have a head function that is safe because the heads can only you can only take a vector of length at least one, and you always return a value. And so this is a language, but this is also a logic. This is the logic behind the proof assistance Lean, ACDA, or COC. And on the other side, we have gradual typing. Here, the aim is to mix together a static and dynamic typing discipline by adding this unknown type inside a static system. You treat this type optimistically during the typing phase. And you compensate this with runtime checks to ensure that the assumptions you made during typing are actually valid. Work on gradual typing has been going on in the last 15 years or so, started with simply typed lambda calculus and went up more and more complex typing disciplines. But nobody has been really able to handle full-blown dependent types yet, and this is exactly what we propose in our paper. As to why you would want such gradual dependent types, well, the answer is pretty much the same as what you'd answer for any other gradual type system, namely incremental development. If you've ever tried programming with dependent types, you know it's quite tricky to handle. When you start writing these kind of functions, for instance, you have a filter function that takes a predicate and a vector, and you want to select the values in the vector that satisfy this predicate. And of course, the length of the output vector depends in an integrate way on these inputs. And maybe you don't want to specify that type dependency before you've even started writing your filter function. And this is where you could now use the gradual typing by using simply the unknown when you're still writing the type of your program, writing what you think is an implementation, and start testing it without giving a fully precise type. That way you can write these kind of examples that would here type check because you have this optimistic assumption that filter returns something unknown, and head treats this as well, something that might be good at runtime. And then you can run it, and in the first case you get an actual legitimate value, and in the second case you realize at some point that there was a lie somewhere, and so you have a runtime error on the length of your vectors. And now maybe you want to come back and actually give a precise type of function. So you can first take that out inside a side definition. And maybe you want to just give the nil case in the first place and not bother with the recursive case. And at that point, you'd be already able to have this example not type check anymore, because now this would be of length 0. So in general, the idea is that you can make your types evolve while you are developing, making them more and more precise. And the key point is this optimistic assumption on typing. This is really a key feature of the unknown that you cannot have with a pure axiom, because none of the examples I've shown would type check if the unknown was just an axiom. So it's really this optimism that is key here. But of course, dependent types are also quite demanding and quite hard. And so there are quite a few issues that we had to solve to bring these to CIC. The first issue is that in dependent types, there's quite a lot of things mixed together. There is no such a clear distinction between terms and types. And as you've seen in the previous example, we really want to use the unknown not only as a type, but also as a term. And of course, this brings quite a few intricate things to solve. Another thing that is kind of mixed together is typing and runtime. In CIC, you need to evaluate arbitrary programs during type checking to compare your types. And in usual gradual typing, this separation between typing and runtime is very important, because you need to elaborate your terms to a language that features these runtime checks before you can actually run them. And so here, this intricacy brings also a difficulty for gradual types. Another pain point are effects. So you've seen already the use of errors for gradual types. And there's also usually divergence involved when you start gradualizing systems. And effects are known to have quite tricky interactions with dependent types. And the last difficult point is maybe the crux of CIC, the so-called indexed inductive types. So I've shown already the vector example, and the prototypical example is the equality presented as an inductive. And I won't have much time to talk about this in this talk. You can go look at the paper for more details. But basically, the baseline here is that the case of vector works really fine, because it's simple enough in a way. It can be expressed as a fixed type. But the equality is somehow harder, and it's currently out of our scope, although we're still working on this. So as a disclaimer, from now on, when I say CIC, think CIC with nice enough indexed inductive types. Now, let me move on to a short overview of what the system looks like. And first, a bit of bad news that we've called the Fire Triangle of Graduality. So if you start to list the properties you'd want from the perfect ideal system, you'd get something like this. First, you have the non-negotiable safety property that decomposes into progress and preservation. This basically says that your programs do not go wrong. And this is something that we're really not ready to abandon as type theoreticians. Next, you have normalization. And this we care about for at least two reasons. First, because together with safety, it entails a logical consistency of the system, the fact that you cannot prove false. And of course, this is important if you want to use your language as a proof assistant. And the second important reason to have normalization is that it entails decidability of checking, because you need to evaluate programs during type checking. And if you may have diverging programs, then type checking itself can diverge. And the last two properties are important more from the gradual point of view. The first one is conservativity. Here, it's in the gradual sense. It has nothing to do with logical conservativity. What this says is that your gradual language has CIC as a subfragment. And on that fragment, it behaves exactly the same as CIC as you know it. So this is important if you want your language to be predictable for people who already know about CIC. And the last property is graduality. I'll talk a bit more about this later. But the idea here is to ensure that you have a smooth transition in the gradual world. If you replace parts of your terms with the unknown and lose in precision, then these terms will still behave in a nice way with respect to the more precise term. And this is really what people in the gradual language community care about. And the sad news is that actually you cannot have all of this at once. Especially if you have safety, you cannot at the same time have graduality, normalization, and conservativity. And the reason is that if you have safety, conservativity, and graduality, then you can embed the pure lambda calculus inside your gradual language. And of course, pure lambda calculus is divergent, and so you cannot have normalization. Now, we cannot have the perfect system, but we can still have something pretty good. And actually, we were able to design one single system that we've called GCIC, for Gradual Calculus of Inductive Constructions, with 3 variants. And each of these variants will keep 2 sides of the triangle while relaxing the last side. And the way we do this is by having a fine control on the universe levels. If you know about proofs of normalization for CIC, you know that these universe levels are really the key ingredients in proving normalization. And here, by slightly altering the way they're treated between the 3 different variants, we're able to control what properties we have and what property we leave out. And more precisely, the first variant that you encounter would be GCICG. This is a system where you have typing just like in CIC, and you have a reduction that behaves like that enables this pure lambda calculus examples. So you have a system that is both conservative and gradual, but it's not normalizing. Next, you can move on to GCIC N. Here you restrict a little bit reduction to have a failure a little bit more eagerly, so that stereotypical non-normalizing terms such as omega would fail at runtime. And you keep typing as in CIC. Here you regain normalization, but what you lose is graduality because some terms do not behave exactly as you'd want them to. And if you want to regain graduality, then you need to have a bit of restriction at typing. So you have to lose conservativity to regain graduality. And the last combination would not be possible because it would endanger safety. But still, apart from these small changes on the universe level, all three systems are designed exactly in the same way. So you can choose depending on what you want and the things you want to achieve, which variant suits you more. Okay, next, let me go to maybe the most emblematic typing rule of CIC, which is also the one that really needs a lot of effort to adapt to the gradual world. This is the conversion rule, and what this says is that if you have a term of a certain type, and that type is convertible to another type, so this is where you have computation appearing to compare your two types, then your new type is also a valid type for your term. And this poses a number of issues in the gradual context. The first one is that this rule only makes sense if you have a transitive relation here, because you can stack it any number of times, and this does not change anything. Because of transitivity, this amounts to just one use of the rule. But in the gradual world, we wish to replace conversion with a non-transitive relation. And of course, now this stacking any amount of rule does not work anymore. And so what we've done here is move to a bidirectional typing discipline that constrains the structure of typing derivations a lot more so that we can constrain the ways conversion is used. And in particular, this rule now looks like this. You can use computation, but only once at the border between type inference here and type checking here. So you cannot stack it any number of times. The next issue, as I've mentioned already, is that computation needs a form of runtime check to be safe. And so we need to somehow mix together typing and elaboration to inset those runtime checks while we're still typing our terms. The picture looks something like this. So we have here our GCIC source language. We elaborated to cast calculus that we've called CastCIC, where you have these runtime checks. And this is usual for most gradual languages. This is usually how the runtime semantics is defined. But the twist here is that we use computation in that CastCIC layer during elaboration to provide computation that we can use to compare times. So the rule actually looks like this. We have this term T that we're now elaborating lives in the source language, and everything else in green is in the target language. And now you see that you've got this extra elaborated term here and here with the extra inserted runtime check. This is how we write them down. And you also see that now the inferred term type and the checked type both live in the target layer. So computation makes sense there, and you can actually evaluate them and compare them using this consistency relation. And the last issue has to do with this consistency relation and with its decidability. The ideal consistency relation would be a form of higher order unification. So relaxing a conversion with a form of unification. And this is an undecidable relation. And if you want to keep type checking decidable, of course, this is not something we can accept. The solution here is to have a form of over-approximation, but we still have to be careful in order to keep conservativity. I'll talk about this later on. And so now the pictures look like this. You have this source language GCIC, which just has this unknown and nothing else. And the really intricacy comes up in the target language in CastCIC, where you have this unknown, also errors, as I've already shown before, and these casts, which ensures that the term T, which has type A, can be used at type B. And the way these primitives work, the unknown, it elaborates to the least precise term in the target language, so the unknown of the unknown type. And in the target language, unknown and error both propagate as if they were errors. So you have these kind of things where when you match on the unknown, you get the unknown back. And the cast computes by induction on its time. So here you have a base case, for instance, you have two base types. You're trying to use a Boolean as a natural number, and this will raise an error. And you'd have recursive calls if you use, for instance, cast between arrow types. And the last interesting thing here is that the cast work as constructors or destructors for the unknown type. So for instance, here you have a value n, which is cast from the natural numbers to the unknown type. And this works a bit as a tagged value in dynamic type checking. And when you cast it down from the unknown to a new type x, then this triggers a check that NAT is actually compatible with x. So that's nice, but of course we want to have properties and theorems about the system, and those we also have. A first batch of theorems are the type theoretic theorems. So we have the progress and preservation properties in CastCIC, the language where those actually make sense. And also normalization, of course, for the variants where we want to have normalization. And these are proven, so progress and preservation by just checking that we can extend the state-of-the-art, the work in Metacoc by Mathieu Sozo and others, on proving progress and preservation for CIC. And as for normalization, what we show is that you can translate back from CastCIC to CIC itself in a way that preserves reduction, so that normalization of CIC entails normalization of CastCIC. Next, we have the so-called static gradual guarantee, which says that elaboration is monotone with respect to loss of precision. So if you replace parts of a term that type checked with the unknown, then you'd get, again, a term that type checks. And this is important if you want your unknown to be predictable. And to be able to do this, we have to introduce a syntactic notion of precision, one that comes before typing, because typing is a consequence of the theorem. And here the key property is to show that precision is a simulation for reduction, so that the two interact well together. And this is a property that had been already remarked in the literature. For instance, that article by CIC and his co-authors show this property in the setting of the simply typed lambda calculus. But of course, here things are much more challenging because you have to take the full-blown dependent types into account. And once you have this simulation property, then you can show that consistency is monotone, and then that elaboration is also monotone. And the last property here that we also want to have is conservativity, for the fact that CIC embeds in a faithful way into GCIC. And this is where we get a constraint on the consistency relation we chose, because to have conservativity, we must show that on the CIC fragment, consistency is the same as conversion. And so that our over-approximation was not too optimistic, and we're still sensible on at least this fragment. And here this is done by, again, using that simulation property. So this is really the key syntactic property relating the gradual properties with reduction. Now, the last thing we want to show is a form of control of the way reduction or evaluation interacts with the loss of precision. And usually this is done using the so-called dynamic gradual guarantee, which says that reduction also is monotone with respect to loss of precision. The issue here is that in our setting, this is a bit not enough, because it allows for a form of degenerate computation. Basically, it does not prevent you from reducing terms to the unknown. And this is actually what has been done in the last attempt to date towards dependent types, the work by Erimondi and others. They've called approximate normalization, and the approximate here is exactly using a degenerate computation a bit like this to ensure that the system remains normalizing. But this is a behavior that we want to forbid. And so instead, we've chosen another criterion from the literature, the so-called graduality property that has been coined by New and Ahmed. And this is a much more semantic notion that says that if you have two types that are related by precision, then the cast from one to the other should form an embedding-projection pair. And this is a much more semantic notion that somehow corresponds to the dynamic gradual guarantee in a simply typed setting, but in the dependently typed one is much more constraining and actually characterizes a good gradual language. And here we cannot because this is really semantic, we cannot rely on the syntactic precision that was used before. So we have to introduce another notion of precision, a semantic one, that we relate to the syntactic notion, of course. And then we show graduality by building models, and especially models where each type is interpreted by an order that interprets the precision relation. And this part we've actually proven in Agda. Okay, that's it for me today. I'll leave you with this quick summary, and I'll be happy to take questions. Thank you.
Good. Let's start with, thank you for that talk. Let's start with a question from online. Theo Winterhalter asks, when you mentioned incremental development, it reminded me of holes in Agda and more generally of existential variables for unification. Could you elaborate on the relation between those and the question mark?
Thank you. That's actually quite an interesting question. I don't know that much about Agda myself, but for existential variables in COC, the way they work is they provide an under approximation on a higher order unification. So they ensure that maybe you cannot find a solution, but you always stay conservative and you cannot go over what is typable. And here we actually go the other way around. We go for over approximation. So maybe we will type check things that actually cannot run. And this is why we have those runtime errors that we can actually raise when we encounter such typing issues. So this is kind of the going the other direction, accepting the fact that we're not we're over approximating and using errors to compensate for this.
Great. So I actually had a question. The sort of the motivation behind this is to make programming easier.
Yeah.
At least the gradual part of it. You didn't say anything about the experience of using this language. Can you give any comment about it?
So we haven't really, we haven't implemented it yet. So we don't actually know how it would work in practice. But the hope here is really to make the programming with dependent types a bit less painful. And especially currently, a lot of people actually use COC, but do not program with dependent types. And if you look at, for instance, the MathComp library, they have vectors, but the vectors are actually lists with the predicates because it would be just too hard to program with actual dependently typed vectors. And the hope here is that we can make this programming a bit easier by kind of letting people incrementally develop rather than having their invariants enforced all at once at the very beginning.
Okay, I thank you. So that brings us to the end of the TOPL session. I will just mention that my tenure as editor-in-chief of TOPL ends this year. So if anybody feels like volunteering for that role, I'm sure that volunteers will be sought. All right, thanks.